Okay, so here's a classic photoelectric effect question. Basically, this is question 31 on page 267 of your workbook. So if you're having difficulties with this one, take a quick peek at this video and hopefully it'll make a bit of sense once you're finished. So the question is pretty straightforward. It's giving you some data from an experiment. And I haven't bothered to put the values in, but the frequencies of the incident light are going to be changed and the stopping voltage is recorded. So in other words, if we just visualize what that looks like, okay, here's a classic photoelectric effect experiment. We're going to have some kind of voltage on there. Light's going to come in, it's going to kick out those electrons, and you're going to get a current going around here. The battery or the voltage here can be supplied to stop these electrons. In other words, it's going to stop them going around and stop them giving you current. And that's the stopping voltage that we're looking for. This is obviously light, and these frequencies can be changed. So they're going to be gradually increased, which of course means you're going to need more and more voltage to stop those electrons. So if you plot this, you're going to get a linear relationship, and the classic linear relationship you're going to get is something like this, going up, and then you're going to get, well, actually it might be a bit steeper, something like this, and then you're going to get a nice straight line that intercepts the x-axis and then intercepts the y-axis like this. So it's a linear relationship between stopping voltage and the frequency of light. That's essentially the experiment. Now the question is asking you, first of all, what is the threshold frequency? Then it's asking what is the work function, and what is Planck's constant. So when you see this type of experimental data, you should right away be knowing, almost memorizing these three values and how they come from the graph. For the threshold frequency, that is going to be the point at which the electron is ejected from the plate. Okay, so that's, in other words, that's the threshold frequency with which it can overcome the work function and get kicked out of the electron. And on here, it's going to be the x-intercept. Okay, so you can either memorize that, in x-intercept. That's your threshold frequency. You can either memorize it, or you can think it through logically. I'll show you something in a minute that gets you thinking about this process logically, but right now just labeling it on here hopefully becomes a bit of a memory. This x-intercept is your threshold frequency. Okay. How can you think about this logically? Well, the other way of looking at this graph, and we've seen this in class, is to say that this y-axis could actually be an energy. Okay, it could be the kinetic energy of this electron, maybe. And if it is the kinetic energy of the electron, then you're going to get the same type of graphical shape. So we could change this to EK max, and you'll get the same linear relationship. So this of course is energy, EK max, and it's the amount of energy that these electrons are going to have. So at the x-intercept, this is saying that they have no kinetic energy. In other words, this energy coming in from light is not enough to eject those electrons. So this doesn't happen. Okay, so this frequency, this energy, is not enough to kick the electrons out, but at some point it is. So if you keep increasing this frequency, as this frequency goes up, all of a sudden it goes above 0 and you do get this electron. Okay, in other words, that's the threshold frequency. The threshold frequency needed to eject an electron from a metal. Okay, that's what it means. So you can either memorize it just visually like this, or you can think it through logically, whatever one works for you. But that's what it is. The x-intercept is going to be your threshold frequency. And I think the value here it gives you, and it tells you the answer obviously in the workbook, is around about 2.4 times 10 to the 14 hertz. So let's put it in brackets, 2.4 times 10 to the 14 hertz. Okay, next one, work function. So the work function, let's use blue. The work function, let's remember what that is. The work function is the energy, essentially, that holds on to the electron in the metal. Okay, so you have to overcome that energy for it to leave the metal. Okay, so let's come back to this scenario here. You're applying a frequency of light to a metal, and if that frequency is low, in other words, if the energy is low, then the electron is not ejected. If the energy is high enough, it is ejected. So in other words, something is holding on to that electron. It's not just going to freely liberate itself from the metal. And of course, if you think about what's going on inside the metal, there are bonds, and metallic bonds. There's an interaction between the protons and the electrons. So there is an electromagnetic force holding those electrons into the metal itself. That's the work function. You have to overcome that first before the electron can even move. So if we just remember that formula, Einstein's formula from the photoelectric effect, he's saying that the energy of the photon coming in, this energy of the photon coming in, is equal to the energy that the electron is going to have, this energy here, we could call that EK, okay, plus the work function. So you have to overcome this work function first before the electron moves. Okay, so that's what the work function is. Now, hopefully from memory you can recall that it's the y-intercept. That's what's going to give you the work function. But let's just have a look at what that means in terms of units. So it's the y-intercept. Now, let's get rid of this EK because this graph is actually stopping voltage. Okay, so it is actually stopping voltage. And if we come back to our formula here, if we're looking at energies, the energy of a photon is HF. The energy of the electron moving is going to be half mv squared plus the work function, which is HF0. So in other words, this work function down here is a type of energy. It's HFO. And if we're dealing with energies, we need, this either needs to be in EK, which would be, if this was EK, this would be in joules, or, what's the other type of energy we know? Well, the units that we use for energy are either joules or electron volts. Okay, and look, we have voltage. So if your graph is in stopping voltage, your y-intercept will give you the work function, but you're going to have to multiply it by E. Okay, so whatever value you have here, multiplied by 1.6 times 10 to the negative 19 is going to give you that work function. Okay, so in this case, it ends up being about 1.2 electron volts. Okay, and that's your work function. Okay, last piece. Let's use black for this. Last piece, again, this is really just memory, but of course you could go through and look at the units. We won't do the dimensional analysis here, but hopefully you can recall, very simple, the slope here is going to give you Planck's constant. Okay, so this is one of those things you just need to memorize. You could go through, do your unit analysis, but the slope is going to give you Planck's constant. This ends up being about 8, I think. Again, depending on the units. 8 times 10 to the negative 10 to the 34, and I've got this in joule seconds. Okay, hopefully that helps. Do some more practice. There's a few more questions in your workbook here. If you want extra practice questions, let me know. But that is, in essence, that's your graphical analysis of the photoelectric effect. see you on the next video.